periodically?
Mr. Mosley.
Henry. Hank, that's right, I forgot. You know what? I bet you could predict using periodic trends where this scientist is from.
England?
He's a British chemist.
Okay. Aren't there any smart Americans?
Not yet, no. So in 1913, Henry Moseley comes along, and he was working with the Rutherford model of the atom because they'd already discovered protons. And the exact work isn't necessary, but he was playing around with the spectra of metals, the colors that they emit when you hit them with large amounts of electricity, or heat for that matter. And he noticed that a different pattern was going to work better. He realized that the number of protons was a better way of organizing the elements in order.
And we've got protons by now, because this is 50 years later than Mendeleev.
Exactly. Rutherford had already discovered the protons, yep. And they actually knew how many protons were in each atom. So he developed an idea, and he called it the atomic number.
Okay.
Which was based on the number of protons. So he basically just ripped off Rutherford's model, Rutherford's work, and said, okay, we now have atomic numbers. They're equal to the number of protons, and we're going to rearrange the periodic table based on
atomic number.
Atomic number, which is the number of protons.
Which makes it nice and sequential. Right.
And there are a couple places in the periodic table, the modern periodic table today, where the atomic mass doesn't work perfectly. It's, based on Dimitri's idea, it was supposed to go up. Specifically, if you look between cobalt and nickel, iron, cobalt, and nickel. If you look at iron, iron is 55.847. Cobalt is 58.933, and nickel is 58.70. So it goes up and down.
Yeah, just a little discrepancy, though, not tremendous.
Just a slight discrepancy, but it makes all the world a difference as far as the trends are concerned.
Okay.
Okay.
Periods. Similar energy levels, similar electron configurations.
And we'll wind up talking about electron configurations very soon,
yep.
Probably the next lecture. We'll get into that. Similar energy levels, we'll talk about that in just a sec. Actually, similar energy levels should look like this. This has one energy level. This period has two energy levels. This period has three energy levels, four energy levels, and so on and so forth.
Okay. 5, 6, and 7.
5, 6, and 7. And some people actually have periodic tables in their classroom that have these numbers written down them. I don't know, it might be Mr. Kane and Mrs. Goswick.
Yep.
Who knows? Next time.
Families and groups.
All right, so there's S, P, D, and F block elements. I guess we could look at this. It turns out, Miss G, where is the S block? I don't see any blocks that look like S's.
Well, an S block, what we're going to find out is 2 electrons fit into the S. So the S block would be that first and second family,
all right,
including helium. You're going to have to move helium over, right, Mr. Kane?
Yeah, I guess helium actually has to come over here for the purposes of the S block. So helium should actually be there so that it's an S.
It's part of the S block.
But then P's...
Well, P's are going to be 3 orbitals, 2 electrons per orbital. That's 6 electrons total. And that would correlate to all that right there. That's the P block,
okay, so these guys
all the way
here,
down. Yep.
And maybe we can highlight that in yellow. All right. D's...
D is 5 orbitals. That's 10 electrons, so you're looking for 10 squares.
This looks like it's 10 squares across.
Yep.
And then F.
F is going to be...
Hopefully that's not my grade.
7 orbitals, 2 electrons per orbital, 14, so you're looking for 14 blocks.
That's actually hard to write that all the way down there, but that looks like 14 blocks across. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, yeah, 14.
All right.
All right, great. And finally we can talk about the number of valence electrons, right?
Yep.
And this is just... if we draw a model of an atom, like here's the nucleus of the atom, here, lots of protons, lots of neutrons. We know, according to our model of the atom, there are orbits that electrons are actually in. The outermost orbit has the valence electrons.
Okay.
Okay. The inner orbits have electrons in them, but we just don't call them valence electrons. Used to be a long time ago, they used to call that thing that overhangs on a house a valence.
Oh.
long time ago, but nobody knows that anymore.
The inner electrons are called core electrons, aren't they, Mr. Kane?
I guess so, yeah. And
Or
that's 'cause
kernel. I've seen that written too.
kernel, yeah,
I
kernel or
prefer
core on the inside. I prefer core also.
Yeah.
Okay. So valence electrons, this is actually pretty easy. This group 1, has one valence electron.
All of them?
All of them, every
All of them.
single one of those, no exceptions, one valence electron.
All right, that's easy.
This group here has two valence electrons.
All right,
All
that's
right.
easy.
Now, the transition metals here, this D block, is a little bit unpredictable, so we just kind of skip over them.
Okay.
And then boron's group here has 3 valence electrons.
Okay.
Carbon's has 4 valence electrons. Nitrogen's has 5 valence electrons. We can almost guess the next
Yeah.
one. This is almost periodic.
Periodic, I was just thinking the same thing.
6, 7, and
8.
then
Well, 8, yep.
8 electrons if you start with neon,
Yeah.
because helium's an exception. There's always exceptions to these rules. Helium only has 2 valence electrons because it only has 2 electrons.
Okay.
But neon has 8. And then just a note here, these guys down here actually belong right there. They're kind of unpredictable also.
Yes.
All right, guys,
All right.
I think that's it.
On to the next one. See you later.
We'll see you tomorrow. Should we make them do something? Jumping jacks. You must now go exercise.